So first, I will give you an instruction to open quantum system and the model we are going to study today. And then we'll show you that we have a phase transition in this model in certain limit, and then using the field theory and exact diagonalization. And then I will use Kerr's formalism to show you how to calculate things analytically, including spectral properties and critical exponents. And then I will show you how to do the finite size scaling using quantum Landry equation. So let's first start with an introduction to open quantum system. So as you all know from undergrad, if you want to describe a quantum system, we need to write down the Hamiltonian. But now, if there's some coupling between the system you are going to study and the external environment, for example, the vacuum, then what will happen is that the coupling will necessarily lose some information into the environment, and then at the end you will not get a unitary dynamics as you learned from undergrad, but it's going to be non-unitary. Here's just a mathematical description. For example, now you have the system Hamiltonian, you also have the environment and the coupling with the environment, and then you can do the unitary evolution as you have learned in undergrad. But now, because the environment is so big and complicated, so we cannot keep track of the state of the environment. So we need to do a partial choice of the environment. Basically, this will be just some information loss that we cannot retrieve from the environment. At the end, you get a mixed state for the state of the system. So after you're doing this, you can see that the dynamics will not be unitary anymore. For example, usually we start from the initial state that's a product state between the system and the environment. And then you, if you do this process, you can see that the density matrix now evolves as a dynamical map. And then you can see that you can always write down this dynamic map as a super operator. This is also called a coarse sum. So now you can see that it's not unitary because there's a sum in front of it. So one question you may ask is, why do we care about open system? One thing is that it's actually inevitable in several fields. For example, in quantum optics, quantum circuits, or cold atoms. Another thing is that even though people from quantum computing will not like coupling with external environment because that's going to give us decoherence. But actually, in some cases, it can be used to our advantage. For example, we can do quantum reservoir engineering by engineer the coupling and the structure of the environment. You can show that sometimes we can engineer the steady state of the system so that it can be some steady state we want. Another thing is that since now the dynamics is not unitary anymore, so you can have some new university classes that does not exist in Hamiltonians. So that's what I would talk about in last slide was a general non-unitary dynamics. Usually we only care about Markovian dynamics. Mathematically, that's just that the dynamical map now is divisible for any t0 from t can be divided into 0 to t prime and t prime to t. Basically, this means that there is no memory effects. For example, the second map t prime to t does not depend on anything happens in 0 to t prime. So usually this Markov approximation works very well when the system environment coupling is pretty weak, and also the environment has a fast decaying correlations, so that the memory effect is very short. Then you can show that if we have Markovian dynamics, the dynamical map can always give us a master equation, a linear Belair master equation. It can be written as this one. This one is a unitary part. That's what we usually say. And this one is a super operator. It comes from the non-unitary dynamics. So then you can see that the dynamical map is just an exponential of this super operator here. Usually I will call this super operator a linear linear. So here are some examples. One thing, so it's for qubit. This is some Hamiltonian of the qubit, and then you can have decay from 0 to 1, for example, that can be described by gamma 1. And then you can have decoherence effects. Basically, it destroys all the off-diagonal elements of the density matrix, and then you have decoherence. If you take 1 over gamma 1, you will get the T1 time, and 1 over gamma 2 will give you T2 time. Then another model, and also the model we are going to study here, is a Driven-dissipative Kerr oscillator. So theoretically, it's described as a linear blade master equation. For here, we have used a rotating frame, so the Hamiltonian is time independent. Then you can see that here we have the Euro harmonic part. Here omega d is the detuning. It's the difference between the driving and the frequency of the cavity. And we have a nonlinear part. It's one half u a dagger a. It can also be written as u times n times n minus 1. So it's actually an all-to-all interaction between photons. And then we have driving. Here the driving is a 2-photon driving. You will put in 2 photons at the same time. And then we have the Euro dissipator that will just describe the loss of the photons. So one thing you may notice is that there is a parity symmetry for this master equation. Basically, the parity symmetry can be written like this. The effect is that now you can take a to minus a and a dagger to minus a dagger. So you can see that now it's invariant under this parity symmetry. Later I will show that this parity symmetry can be spontaneously broken, and then you can have a second order phase transition. So experimentally, there can be various platforms that can be used to realize this model. For example, the semiconductor microcavity or superconducting circuits. And also, the reason we started this model, as later you can see that as U gets smaller and smaller, there will be more and more photons in the cavity. So actually, this model can be viewed as a quantum matter body model instead of a few body model as you seen from the qubit example. So before we start, I'll give you some theory. Let me show a quote from Sidney Coleman. The career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction. So here, in this talk, I will show you how we can treat this anharmonic oscillator using ever-increasing abstraction. So let's first start from Mean-field theory and exact diagonalization. So for the Mean-field theory, you can start from the Heisenberg picture. Then you can write down equation of motion for the expectation values of A. You can see that basically everything is linear except the one from the Kerr nonlinear part. Then you can use Mean-field approximation by writing this correlation as a product. Here I will denote this expectation value as a complex number alpha. Then you can basically solve this equation and then get the steady state by setting the right-hand side equals 0. And then you show that the solution is given here. Here U is the interaction strength, N is alpha squared. That's the occupation number or the number of photons. So you can see that there's actually a best stability for finite detuning. But here detuning, it can be tuned. So as you can see, if we set omega d equals 0, we have a solution like this, which is a second order phase transition. The order parameter I will denote as phi is U times alpha squared, or U times the occupation number it's 0 below, when the driving is smaller than gamma is a decay rate, but it can be non-zero when G is larger than gamma. So one thing is that you notice that the order parameter is U times the occupation number. So this order parameter is a finite constant. You can, but we know that the occupation number should be proportional to 1 or U. So if you take U to be very small, for example 0, then you can say that the number of photons will diverge in the cavity. So that's the limit of the thermodynamic limit. Then you have some many-body effects. So one thing we can understand how we get phase transition in this model is use the PT symmetry. It's I will not go to details of the PT symmetry. You can read it here in this very nice review. I will just give a very simple example that's useful for us. For example, you can write down a non-Hermitian matrix. Here, sigma z and sigma x are Pauli matrices. You can see that there's an imaginary factor to make this Hamiltonian non-Hermitian. But even though this Hamiltonian is non-Hermitian, you can see that it can have real eigenvalues. You can show that the eigenvalue looks like this. You can say if the non-Hermitian part is smaller than the Hermitian part G, then you can say that these two eigenvalues are real. But if the kappa, the non-Hermitian part is larger, then you can say that this guy is imaginary. So for us, we can write down the equation of motion, the midfield equation of motion using a matrix form. We can say that the matrix form has a matrix part and a constant part. So if you compare this matrix part and this non-Hermitian matrix, you can say that they look basically similar. And then you can show that there's always a parity time symmetry. So here the parity is just by an exchange of alpha and alpha star. So basically, under this transformation, this term will go here and this term will go here. Then you can say that there's a minus sign. The time reversal symmetry is just a complex conjugate. Then you get another minus sign from this imaginary constant I. So now it's invariant and PT symmetry. And then we have eigenvalues looks like this. So it will be just a constant plus or minus this constant from the by diagonalizing this matrix. You can show that it looks like this one. So one thing is that since we want to know the steady state, we can get the steady state in a very long time evolution. So in that sense, only gamma plus matters because gamma minus is always smaller than gamma plus. You can show that the value of the gamma plus as a function of phi and the driving strength G. Here you can show that there are two regions. In this one region, gamma plus is always negative, but in this region, gamma plus is always positive. So if gamma plus is negative, you can say that by doing an exponential, you can show that the value of phi will just decrease exponentially. And then, which means that phi, the order parameter, will also decrease as time evolves. So basically, I show the time evolution process using arrows. You can show that in this whole region, because gamma plus is negative, phi will just decrease in time evolution. But in this part, gamma plus is positive, phi will just increase in time evolution. At the end, what you have is a stable solution along this line when gamma plus is 0. Then you can show that this is exactly what I have seen from midfield theory. This line gives you the midfield solution here. So now we have seen things from midfield theory. Now we want to confirm it using quantum solution, right? So one straightforward solution is by diagonalize the linear blending numerically. So there are some properties of the linear blending. So it can be diagonalized like this. Here it's the eigenvalue and the eigenstate. You can show that the eigenvalue is always non-positive, because if it's positive, things will just diverge. The density matrix will diverge. But there's one more thing, is that there must be at least one lambda 0 equals 0, because otherwise everything will just decay away, and then you cannot preserve the trace of the density matrix. So the eigenstate that has eigenvalue equals 0, that's going to be our steady state. So we can just show the diagonalize the linear blending and show that U times N is actually approaching the midfield theory. Here I show some data for different 1 over U. You can see that as 1 over U goes to infinity, the thermodynamic limit is reached, and then the solution from exact diagonalization will approach the midfield theory. So you can show how they approach the midfield theory by doing a scaling analysis along different points. Here I show you some examples. Below critical point, here I set gamma equals 1, so the critical point is G equals 1. You can see that below and above critical point, as U goes to 0, U times N will just approach the midfield prediction. One interesting thing is that at the critical point, here, there's a very nice power law scaling between the outer perimeter and U. So you can show, I will show you later exactly that we can calculate this exponent. You can show that this exponent is exactly 2 over 3. So I mean, now we have the outer perimeter. Now because we have the exact diagonalization, we can also look at the eigenvalues, because we know from phase transition or Hamiltonians that the system will become gapless at the critical point. So here similar things happens. Below critical point, you can see that the real part of the eigenvalues will become gapped. And then at critical point, the eigenvalue will become gapless because there will be a lot of eigenvalues have 0 decay rate. And then above critical point, what you can say is that the system is still gapped, but there's one eigenvalue that approaches 0 exponentially fast as 1 over U goes to infinity. So which means that we actually here in this regime we have a doubly degenerate steady-state manifold. So as we can see later, this will give us the symmetry breaking of the parity symmetry. So here I plotted the Wigner function of these two steady states. So here the parity symmetry will just transform x to minus x and p to negative p. You can see that this steady state is symmetric and the parity transformation, but this steady state is anti-symmetric and the parity transformation. So now we can show that actually this guy is going to be anti-symmetric, while the one that's 0 here, that's always symmetric. This is the symmetry breaking in the thermodynamic limit. So, okay, now we can be pretty sure that there's a phase transition in this simple model. We can go ahead and try to calculate things analytically using Kerr's formalism. So let's give a very simple introduction to Kerr's formalism. If you want to know more, you can always go to this review paper. So as with every field theory, we start from a partition function. Then after writing down the form of the partition function, we can basically go ahead and calculate things. Here the partition function is just going to be defined as a trace of the density matrix at time t. Later we will send t to infinity, so we'll have the steady state. Now we can just factorize this exponential by assuming that we have a very small time step. And then another thing is that we can insert the coherent state basis for every time step. Now, because it's a density matrix, we have both the cat and bra part. So we have two branches, alpha plus and alpha minus. One thing you want to know about the coherent state is that there are some over-complete bases, and then it's an eigenstate of the operator A. And also, for different coherent states, they are not orthogonal. There's always some overlap between two coherent states. So if you just put in the spaces and then acting the superoperator L on alpha, you can basically transform the superoperator into complex numbers. Then you can then you can basically show that the partition function can be written like this. This is a functional integral of alpha plus and alpha plus star, alpha minus and alpha minus star. Here is an action. You can say that the action has a time derivative part, and the part comes from the linear blending. This is from the Hamiltonians by replacing A and A dagger by alpha and alpha star, and then here it's a superoperator in the linear blending. So okay, now we have write down the action. So one thing it's very useful in doing calculations is to transform it into a new basis. This is just a simple unitary transformation. We can define alpha plus plus minus alpha minus as alpha classical and alpha quantum. Here it's called alpha classical because it's a summation between the two branches. Basically, that's like diagonal elements of the density matrix, where the alpha quantum is the difference between alpha plus and alpha minus. That's like the off-diagonal elements. So then you can say that in this new basis, it looks like this, similarly as the one in the original basis. Here in our model, the Hamiltonian looks like this. This is the driving. It's quadratic, but we have the Kerr nonlinearity that's not quadratic. It's quartic. So now we can try to solve this action. So one simple and straightforward thing to do is to solve the side point solution. As expected, the side point solution will give us the near-field solution. It can be, you can show that alpha classical is just square root 2 times the alpha from near-field solution. There's a factor square root 2 because you can see here that it's not an average over alpha plus and alpha minus, but it's square root 2. So there's an extra factor. So and alpha quantum equals 0. So okay. So one thing you may want to notice is that now it's the saddle point will give us the near-field solution. So how do we get some quantum effects? The thing is that you can do some observation of the nonlinear part, because for quadratic action you can do anything. Well, you can do some observation of this non-quadratic part. You can see that this non-quadratic part is proportional to U times alpha classical squared. Remember that U times alpha classical squared is our order parameter. So this term is 0 below critical point, and it's a finite number above critical point. So how can we deal with that? So we can do some expansion around the saddle point. Then you can show that the fluctuation around the saddle point will give us a new action. This action, the Gaussian part, will look like this. Now there's some modification because it's an expansion around the saddle point. We have effective detweening. That's different from the original one, and also the driving is actually different. The driving now has a modification from the saddle point solution alpha classical bar. So you can show that this driving is always equals gamma above critical point. So now you may question what about the non-Gaussian part? You can see that the non-Gaussian part always has a form like this. One is a cubic term of the fluctuations, the other one is a quartic terms of the fluctuations. But look at the factors. So we know from the set point solution that alpha classical is actually proportional to 1 over square root u. So if you look at this term is of order square root u, where this term is of order u. In the thermodynamic limit, we will send u to 0. So this non-Gaussian terms will just vanish. So at the end, we will just need to worry about the Gaussian terms. Later, I will show you how can we study finite size effects by doing some analysis of this non-Gaussian part. But if we want to look at the thermodynamic limit, only the Gaussian part matters. Now, with the axiom, we can calculate the Green's functions. That's the standard thing to do. Here we can look at the Kerr's advanced and retarded Green's functions, defined as correlations between classical, quantum, and quantum classical. You may wonder what about the correlation between quantum and quantum. That's exactly 0 for any linear blending because of the structure of the axiom. So, for example, you can calculate some observables from the Green's function. One thing is that here I write down the Green's function as a function of t1 and t2. You can show that in the steady state, it will only depend on the difference between t1 and t2. I will denote that as tau. So, for example, the coefficient number can be calculated by setting the difference to be 0. You can see from the output form that this one is just 2 times a dagger a plus 1. This will give you the coefficient number. And another things are some spectral properties of the system. You can look at this diagram here. For example, we can send a very weak signal to prove the system. You can see that then we can measure the absorption probabilities for some frequency of the proof. This will give us the spectral function. It can be written down as basically a real part of I times GR. Another thing we are interested in is the output light. Basically, the photons, the properties of the photons that are dissipated from the cavity. For example, we can measure the power spectrum of this dissipated light. From input-output theory, you can show that this output light can be written as square root gamma times A. A is the field in the cavity. So now we can basically write down this power spectrum as a function, basically as a form of the spectral, as the Green's functions. Because as we have seen, all the Green's functions can be calculated analytically because it's a Gaussian theory in the thermodynamic limit. Here I show some results. For example, this one is the spectral function very close to the critical point. We can show that there's a very sub-peak, and then there's a very small bottom, that's a Lorentzian. Later I will show that this very sub-peak will be a directory function. This is the signature of the criticality because it has a very sub-peak, which means the correlation or the coherence time will just diverge. For example, here I show the width of the peak. You can show that as critical point is reached, the width will just decrease until 0, and then above the critical point, it will just increase again. So this is an example above critical point. You can show that now the peak is shifted away from 0. The reason is that, as we have seen actually, so this is due to the effective detwinning, as we have seen when doing an expansion around the settle point. Here is I plotted the peak position as a function of the driving. you can see that below critical point it's always peaked around 0, but as G is increasing, there's a symmetry broken. It's not peaked around 0 anymore, but it's this peak producing is actually defined by the effective detuning negative 2 pi. So another thing is the power spectrum. So here I show the inelastic part of the power spectrum for several different drivings, as expected, because there's a effective detuning. It starts from a peak that's around 0, and then gradually there will be 2 peaks. So now we have seen everything in the thermodynamic limit when U basically is very small. Now, one more thing. So with in this thermodynamic limit, we can always calculate the critical exponents using the exact expression, for example, for the occupation number and also for the correlations. As we have seen, the occupation number is proportional to 1 over U. So we expect that as a critical point, it will just diverge. So we want to say how it diverges. So you can, as we have seen from the Kerr-Screen function, you can calculate the occupation number exactly. You can show that around the critical point, it will just diverge as 1 divided by gamma minus G. Similarly, you can look at the dynamic critical point. Dynamic critical point is just a measure of how the correlation diverges at the critical point, or in other way, how this decay rate vanishes. Can show that it's proportional to gamma minus G. So the correlation length will be just 1 divided by this decay rate, which is the same as divergence over the occupation number. So now everything is in the thermodynamic limits. We can also study the finite size scaling using quantum Lagrange equation. So I will show you how to derive the quantum Lagrange equation from the Kerr's formalism, and also show the finite size scaling. So, okay. So one thing is that for simplicity, we can choose the driving strings to be I times a real number. I mean, you can choose arbitrary phase for G. Here, we just use this one for simplicity. Then, actually, for this driving, you can see that actually the two variables will behave very differently, even though alpha classical matters and alpha quantum equals 0 in the midfield theory. You can show that for this driving strings, only the real part matters, while the imaginary part actually is squeezed. So then you can, I mean, this is another coordinate transformation of the original basis. So we can write down the xn in this basis of x and p, and then you can do Hubbard-Stoyanovich transformation to get rid of the x quantum and p quantum part. And then you can say that we can get a Lagrange equation. So to say why it's a Lagrange equation, you can say that there's no second order derivative of x classical. This first order derivative is just a friction. Basically, it's a massless. It describes a massless particle with some friction and some quadratic some quadratic potential and some noise. Then if you want to solve the steady state of x classical and p classical, you will get an effective sum distribution of them. For example, for x classical, the distribution of x classical is just given by this sum distribution. Here, the free energy is given by this quadratic potential. It's just harmonic potential. And the effective temperature is gamma divided by 2. It comes from this noise. So one thing you may notice that as at the critical point, gamma equals G. This guy just vanishes. So it's a very flat trap. Then you can say that the variance of X classical will just diverge. And the occupation number is actually proportional to X classical squared. So you can see that why the occupation number will diverge at the critical point. So here it's still a theory without the nonlinear part, because in the thermodynamic limit it doesn't matter. But if we want to study the finite size effect, we can add the non-Gaussian term. I will not go to the detail. It's basically a comparison with the saddle point solution and a process of getting rid of some irrelevant terms. Then you can get another Langevin equation. Now this Langevin equation has a new term. This term is not quadratic. It's x to the power of 5. You can see that this guy is proportional to u squared. So when u goes to 0, this term does not exist. But for any finite size effect, u is not 0. This one will matter. So now you can see that the free energy has a higher order potential. That's x classical to the power 6. You can see that as at the critical point, gamma minus g is 0. This term is just vanishes, but this term is proportional to u squared. So for any non-zero u squared, it will give you a trap that will make x classical squared not diverging anymore. So starting from this equation, we can just calculate the finite size exponent. For example, for the occupation number, it's proportional to x classical squared. You can show that the distribution will just give you a scaling that's 1 over u times to the power 2 divided by 3. Here are some data from exact diagonalization. You can see that there's a very nice relation between n and 1 over u to the power 2 divided by 3. Another thing is that we can look at the scaling of the gap or the divergence of the correlation function as thermodynamic limit is reached. For example, we can start from this expression. Here we are assuming that tau is very large, so it will become an exponential decay. Then you can put this back into the quantum Langevin equation. You can show that this decay rate actually proportional to u to the power 2 divided by 3. The exponent is the same. You can see that as u goes to 0, kappa will just vanish, and then we will have a divergent correlation length. That's because it's proportional to 1 divided by kappa. So here I show the scaling of the gap as u goes to 0. You can see that for small u, there's a very nice power law relation. So, okay, in summary, we have seen that there's a Driven-dissipative phase transition in a very simple Kerr nonlinear oscillator using near field theory, exact diagonalization, Kerr formalism, and quantum Langevin equation. So we have shown some spectral properties at the thermodynamic limit. For example, the spectral functions and power spectrum. And we calculated the critical exponent for the occupation number and the dynamic critical exponent. They are both 1. And then using quantum Langevin equation, we calculated the finite size scaling exponent. They are both 2 divided by 3 for the occupation number and the gap. So finally, I want to thank my advisor, Harold Brahunji, and thank for the funding from DOE, BNL, and Duke. Thank you.
Thank you very much, Xin. It's a very nice presentation. And any questions for Xin? Our audience? I have at least one question. So okay. in the thermodynamic limit, it seems the mean field description works pretty well, right? Mm-hmm. So do you think it's possible to break this mean field description, maybe by adding extra terms or by making the correlation making the driving very strong? Do you think that's possible?
Okay. So That's a good question because I mean, so the theory works for any driving strings, but actually you can see how the midfield theory will just fail here. If you have a detwinning, actually you can see there's some gap between these two branches. It's a bistability. That's because here actually there will be some, we will have ignored the fluctuations. The fluctuations will induce some tunneling between this solution and this solution. So actually if you solve the quantum solution, it's not going to be a best stable solution. It's going to be a first order Friese-Anderson, basically 0 here and then now 0 here.
Yeah, oh, I see. Yeah, I already missed it. So in the discussion below, we always assume detuning is 0 to have a second order.
To have a second order Friese-Anderson. Right.
Okay. Any other questions for Xin? Okay, I actually have one more. Do you think that's possible to have time-dependent driving in G, so that at least factor G is now carrying a time dependence, and then we kind of make it a non-equilibrium system?
I mean, this is non-equilibrium, right? So there's always a
this is already non-equilibrium, but maybe we could have some quenching like
right. Here, here we only started the steady state for the for fixed driving strings. I mean, actually, if you don't look at the steady state, there's always some quenching, right? You start from some initial state, then you start the driving, then there's a quenching process to approach the steady state, right? So I mean, you can't add a time dependence here to look at the, for example, look at the deviation from the steady state. It's also a very interesting problem, yeah. But we didn't do it here. We just look at the steady state properties.
I see. I guess in that case, it's harder to think about a mean field solution unless there is some kind of periodicity in G. In time, maybe they will have used.
I mean, it may still work, right? So as long as fluctuations will not matter that much. Yeah.
I see. Okay. All right. If there is no further question for Xin, let's thanks Xin again for his nice presentation, and thank you for joining our CSIQ seminar today.
Thanks.
Yeah. Thank you very much, everyone.
See you.